So yeah, hi, I'm Francesc, and first of all, thanks so much for inviting me to be here. It's an honor. First time in Israel, and I'm loving it so far. So thank you so much. Today I'm going to be talking about contracts and interfaces. So how many of you have heard about Go contracts? Okay, so I'm going to introduce what they are, and actually what they are. They're nothing. What they could be one day, and why they actually are similar to interfaces, but we're going to be talking mostly about interfaces today. So we're going to be talking about what interfaces are. Then we're going to start talking about the generics draft. Go has been talking about generics forever, and finally it's a thing that we can actually see, and there's code that has generics in Go, which is kind of weird, but you'll see. You might like it or you might not. And there's two parts of it, type parameters and contracts. And then we're going to compare them and see which ones are more powerful and which ones you should be using or maybe not. So, first of all, what is an interface? Is the mic working? It's doing weird things. Oh, okay, cool. I'll continue. So what is an interface? So yeah, according to the source of all truth, which is kind of over here, is the Wikipedia, by the way, it says that in object-oriented programming, a protocol or interface is a common means for related objects to communicate with each other. What does this mean? First of all, it's about communication, right? It's about different pieces that are talking to each other in some way. And an interface is what describes what is possible, or what you allow in that communication. And then unrelated objects, right? There are two things that might not know each other completely. Everything they need to know is the interface. And that is the power of it. It's actually separating some communication in different pieces that are completely independent, because you're specifying the communication rather than the people communicating or the processes. So for me, the best example of an interface is this, Lego. Why? Because you can buy Lego, and what a piece of Lego is, it doesn't know it, right? It really depends on how you use it, and it just composes really well. And Go is about composition. So actually, interfaces is a great way to do composition. But of course, if I tell you, well, a Lego piece looks like this is not enough, right? You actually need to specify it in lots of detail, so then it will actually match one piece with each other. And this is a little bit of the idea of interfaces in general. There's one interface that is incredibly powerful and incredibly successful, Docker. And I'm using containers because that's what you do. So why is this an interface? Well, because actually what you're doing with Docker is basically you're creating an interface around what a process is, what it's allowed to do, and then that allows you to create tooling that knows how to handle a process, a container, no matter what's inside, right? That idea. And that actually comes from the idea of these containers, which are also an interface. The boat doesn't know what's inside of the container, and the container doesn't care whether it's in a boat or in a train, right? That's the whole idea of interfaces. So that is what is an interface, but what is a Go interface? So in Go, there's two kinds of types. There's abstract types and concrete types, and that's it. All types are either abstract or concrete. So concrete types in Go are the ones that we use all the time. So if you think about integers or booleans or strings, and they actually represent, they tell you what a piece of memory looks like, right? So when you have an int64, you know exactly how long it is, you know how you can use it, etc. And normally what you do is you attach behavior to those concrete types, which unfortunately I'm not sure you can all see, but basically there's a method called positive then defining a number, which is a type that has the same thing as an integer. So why is this interesting? Well, because there's the base, right? Like we are using concrete types all of the time. You could write perfect programs without having a single abstract type, just with concrete types. So all of these are concrete types. Pointers and pointers to structs and slices and maps and all of these things that we use all the time, those are concrete types. What are abstract types? So abstract types are the others, are the interfaces. And this is actually interesting because rather than describing a layout in memory to which you attach behavior, they describe behavior only. you do not know what's behind a reader. It could be an empty struct, it could be an integer, it could be a buffer of bytes, right? You do not know, and actually you do not care, and that's the power of the interface. And the idea is that you define a set of methods, and by that set of methods you're describing the behavior. So, two interfaces that I'm sure you've all seen, reader and writer. And in reader you say, this is something I can read from, and these are the method type. And writer, it's the same thing, but the other way around. You can write into it. Cool. So actually, if you think about it, by describing the set of methods they need to satisfy, you're creating a set of types. So if you think about that interface as a proof of membership to a set, you can see that, for instance, gzip.writer is an IO writer. It's part of that. But strings.reader is not a writer because it doesn't have that method. That write method instead has the read method, and it makes it be part of the reader, IO.reader set, which means that it satisfies that interface. And now the cool thing is that once you start thinking about them as sets, it just makes sense if you know how sets work. So if I tell you that I have a union of interfaces, what I'm saying is defining this read writer, which is all of the interfaces that have both read and write, which you can write like this or like this. This is exactly the same, and this is actually how it's defined in the IO package. If you define it like this, now the interface, the union of interfaces correspond to the intersection of the sets, right? And this makes sense. And now if this makes sense, what is that? What is the rest, right? What is the thing that contains all of the types? Yeah. The empty interface, because the empty interface is the one that has no methods, therefore all of the things are there, which it also happens to be the intersection of the interface writer and reader. They have nothing in common, so their intersection is the empty interface, which corresponds to all of them, all of the types. And this is what you're doing when you're working with interfaces. You're defining sets of types and working with them. So this is why Rob Pike, when he says the empty interface says nothing, it doesn't mean that it doesn't say nothing because you lost all your type data or whatever. The data is in there. But what you're saying is that if you say, hey, I'm going to give you an empty interface, you're basically telling me that you're going to give me something, but you don't really know what, and good luck, right? So this is not very useful. So that's why the empty interface is awesome, but also don't use it that much. So why do we use interfaces at all? There's three main things. One is writing generic algorithms. And this generic is interesting, because these generic algorithms is not generics like in C++ or in Java. The fact that it's generic and the algorithm works on many different types. Interfaces allow you to do this. Also hiding implementation details and providing interception points. And we'll get to those two a little bit later. So, little Paul. If I give you these four functions, the first one receives a pointer to a file. The second one, a read-write closer. The third one, a writer. The fourth one, an empty interface. Which one is better? Let's see. C? Everyone is saying C. Anyone for A? Anyone for B? Okay. Anyone for C? Okay, most people. Anyone for D? Me, because why not? So actually, clearly, A is not the good one. Why? Because how do you test it? Right? To test something like this, you actually need to create a pointer to a file. And that's hard. And what's the point of creating a pointer to a file if you don't need it? Empty interface. The cons is that, how do you even write to an empty interface? Well, how do you do this? Also, it requires runtime checks. You're going to need to check, is this really an interface or not? And the only pro is that you can do really bad code. If that's your goal, great. But other than that, do not do that. So what about between B and C? Well, it depends, right? If you're calling it write to, probably you're in a writer, but maybe you need to close that writer too. So maybe you need a write closer. And maybe you're reading, so you need a read-write closer, but in that case, you should change the name of the function. So it really depends on what you're actually doing inside of that function. But these two make more sense. Why? Because you can actually replace it with anything. You can pass a buffer of bytes or a string or whatever and make a reader out of those, which allows you to do testing much easier. So back to Rob Pike, he says, the bigger the interface, the weaker the abstraction. And if you think about this thing of the bigger the interface, the weaker the abstraction, it kind of makes sense, but it's kind of misleading at the same time, because the bigger the interface, the weaker the abstraction. What it means is the more methods you add, the smaller set of types you can accept, right? Which means that the abstraction is not as powerful because you can work with fewer types. But at the same time, when you have a very, very tiny interface, which is the empty one, the abstraction is huge, but completely useless. So you need to take a little bit that into account too. There's one of the solid principles. There's a talk by Dave Cheney on them. They're really good. And one of the robustness principles is, so the robustness principle is this one. Be conservative in what you do, be liberal in what you accept from others. And this is, I think, something that was written talking about TCP, which is basically what you are sending through the network, what you're receiving. Good luck, you don't really know what you're gonna receive. Try to be nice, right? We can also think about it in be conservative in what you send, be liberal in what you accept. So let's talk about abstract data types. Has anyone heard about this thing, abstract data types? Okay, not many. So abstract data types is a very useful mathematical way of thinking about types in general. So basically the idea is that it allows you to define the possible values and their behavior, and then some axioms, or some rules that define how those types work. Those values interact with each other. And traditional example is stack. So if you think about a stack, if you push into a stack an element and you get the top, you should get that element back, right? This is a rule that doesn't talk about what S is. This stack, we don't care. It's whatever it is. I don't care how you implement it. There's a rule, an action. When you pop after pushing an element onto a stack, you get back the same stack. So all those ones that you can create, when you create a new stack, it is empty. When you create a new stack and when you push something onto a stack, no matter what that is, it will not be empty, right? So all of these are rules, and they give you behavior of a type. And this, you can think about all of these actions that define what a stack is. And this, I think, that it defines exactly what a stack is, by the way. Those 4 actions just define completely what the behavior should be. You can think about it as an interface, right? So you say, okay, so when I have an abstract data type, like anything that is a vector, a queue, a stack, whatever it is, you can actually represent that as an interface. The problem is that, so the good thing about this is this allows you to write a lot of different algorithms on top of this. So for instance, if you have this stack interface where you can push something, pop something. Oh, I'm missing top, by the way. That's the only method that is missing. Then you can do things like, what is the size of the stack? And you can write this algorithm that receives the stack and checks whether it's empty, and it figures out how many elements were in that stack. This doesn't need to know what a stack is. Why? Because the stack is the interface. It's the result of doing that abstract data type analysis. This, you might have seen it. It's exactly the same idea. If you want to be able to sort something, these are the 3 things that the abstract data type of sortable requires. And these actually in the sort package, right? So when you have less, swap, and len, these are the 3 things. Then you have sort, stable, and is sorted. Those algorithms are able to work abstractly in a generic way on top of those types because you define that interface. And this is really powerful, but it has limits. What about read and writer? You have reader, you have writer. So you can do the same thing. You can actually now consider that writing something into a writer is an algorithm, which it kind of is. You can say, well, I'm writing whatever into the writer. I do not care what the writer is, because I've defined what the behavior should be, so then I'm good. So I have my interface that corresponds to behavior. I'm able to use it. Great. Is this enough? So think about reader. So reader is something that has a method read, plus all of this. This is the documentation for the reader type in the IO package, right? And it says a lot of things, and you need to match every single one of those in order for your reader to be an actual reader that will work well with the rest. Why is this? Well, because actually, out of all of the actions that I mentioned at the beginning, those actions are not necessarily translatable into an interface. The type system of Go is not powerful enough for this. If you were using things like maybe Haskell, maybe you could do it. What is the solution for this? Unit testing. The actions can be transformed into unit testing that work on a slice, on an interface. So then you can say, I'm writing my thing, matches the type, and then I pass the unit tests. And now I'm pretty much sure that what I've implemented is actually a good reader. And this is something that, for instance, the SQL package does. Defines an interface they need to satisfy, and then you have a bunch of types that will make sure that what you wrote was correct. So, with interfaces, you can write generic algorithms. And this is great. So what about the other side? Be conservative in what you send, be liberal in what you accept. Another poll. What function do you prefer? Function new returns a pointer to file, returns a read-write closer, returns a writer, or returns an empty interface. Let's go with A, okay, B, C, and D. Okay, yeah, he was scratching his head. I was like, whoa, no. Many people did not raise their hands, and this is interesting, right? Because this is a little bit confusing. What about this one? This one is the best, right? Because the good thing about this is that if I'm returning this, you can use it however you want. If you want to use it as a writer, just assign it to an IO writer. If you want to use it as a read writer, do that, right? It's completely up to you and giving you the freedom to do so. And the good thing is that in Go, it's super simple to do. You just need to assign it to the variable. That's it. So the B and C are not the good ones, except that we'll talk about why they actually are the good ones later. So yeah, be conservative in what you send, be liberal in what you accept. Return concrete types, receive interfaces as parameters. That's basically the robust principle applied to Go once you understand how interfaces work. Cool, so is this true? No. This is true most of the time, but not all of the time. Because what if you actually hide the implementation details? What if I want to give you something, but I don't want you to depend on the values on the fields that are inside of the struct file, right? It's something that might change later on. I don't want you to depend too much on that yet. Have you used this package? The context package. This is probably my favorite package in the standard library because it's super simple, very elegant, and the implementation is amazing. The implementation inside is super cool. I recommend actually reading the whole thing. There's some lines of code that's like, beautiful. Also, I have a justforfunc episode on it. I love it so much that I did the whole thing. So before the context package was part of the standard library, it was implemented at Google internally as part of something that we used to pass things through the network. And it looked like this. You had the context interface and one concrete type, the lowercase context, that satisfied that interface. And there was one single one. And the problem is that one single type did all of the things and actually did not scale really well because you have many copies and ends up being a very large object really fast. So that was not perfect. So later on, it became like this. So in here you have the empty context that doesn't do anything, and that is perfect because it's an empty interface. It's an empty struct, so no space in memory. You have something to manage cancellation, something to manage timers, something to manage values. And the four of them are completely independent. The four of them satisfy the context interface. You do not need to know this. And the best part is that if you start working with the context package here, and then you migrate here, you did not notice, right? So having an interface actually has a lot of power, especially when you have something that is going to be really basic to a large infrastructure. Having the details of it can make it so it scales better in general, and it evolves better. So yeah, interfaces hide implementation details, and this is why interfaces are so great. What about call dispatch? So have you ever heard about what call dispatch is? If you heard, raise your hands. Okay, not many of you. So these are call dispatch, f.do, right? It's a function call. It's a method call, actually, not a function call. Why is this a call dispatch? Well, because what you're doing is you're dispatching the call of do depending on what f is, right? There's two different kinds. On concrete types, it's static. If I have os.file and I call write, at compile time I know exactly what that means. I know exactly what piece of memory I'm going to be going to and what piece of code I'm going to be executing. Because it's a concrete type. And it is very efficient, and you cannot intercept it, because actually this gets translated as a jump to an instruction, right? That's it. You don't have any opportunity to play with that. But with abstract types, this is dynamic, which means that you do not really know what you're going to be calling when you're compiling. It will be decided later on, right? And this means that it's less efficient, because it needs to do some jumps. But in one of those jumps, you can actually put stuff in between. And this is incredibly useful. Why is this useful? Because it allows you to add behavior to something that is already defined without having to modify that code. So let's think about one example. So the client package so the HTTP package has the client type. And the client type is a struct. It has a field called transport, which is of type round tripper, and round tripper is an interface, which is called round trip, receives a request, sends back a response. Why is this? Why do we have this? Well, actually, that is the perfect example of an interception point. It allows you to extend the client type without having to modify the code in the standard library. Why? Because you cannot. So it's easy. So if you had HTTP client and you have a default transport, this is the default behavior, right? This the default transport is the default round tripper, and it does the normal thing. So when you do HTTP get, what you're doing is you're getting a default client that calls a default transport. Easy. But you can do things like this, and you don't need to get too much into detail. But here I'm defining a new struct that has a round tripper in it, and also a bunch of, it has a map of string to strings, and those are the headers. And what I'm going to do is I'm going to implement the round tripper interface. So round trip is going to be adding all of the headers to the request and then sending it through, right? So once you set it up, so here I'm setting a client that uses as transport this headers transport that I created, and then that headers transport uses the default transport. So it looks like this, right? So I was able to intercept that call and put something in between. And now this means that when I'm calling, for instance, get golang.org, I'm actually going to be passing also the headers foo equals bar, right? I do not need to think about that anymore. I just define it, and it just works. And that's the power of the fact having those interception points. And this, you can see it everywhere in the standard library. Actually, my piece of advice is if you're using any package in the standard library, look for the interfaces, because those are the places where you have the power to change things. The rest, you cannot change anything. The interfaces that are defined, that is the points where you can add more behavior. So you can also change interfaces, right? Like if you can put one, you can put many. So for instance, we have something here. This is actually written in Hebrew, for real. It might look like I'm making fun of Hebrew. No, I do not know how to say it, but this is Hebrew. And what we're doing is we're going to get a reader, a strings reader, that's going to read from that input, which is a string, that returns a reader. Then we're going to do base64 decoding from that reader into a reader. And then we're going to do a gzip reader from the reader into another reader. And then we're going to copy from the reader to the standard output. So this looks like this. You have that. You create the strings reader, then the base64 decoder, then the gzip reader, and then you pass it to IO copy. IO copy doesn't care at all. IO copy doesn't care that there's all of this chain. It's just a reader. And every single one of the readers doesn't care about what's around. It's also a reader. And that's the whole power of the interfaces. Then if you write it here, this will say this, which I have no idea how to pronounce. I think this is shalom, but I'm not sure. OK, good. The rest, I have no idea. Could someone pronounce it? No, but in Hebrew. Ah, really? Shalom gophers? Oh, easy. OK. Google doesn't do pronunciation of Hebrew yet, apparently. So yeah, interfaces provide interception points. It is something really, really useful for when you're developing large systems and you can add new behaviors later on. So yeah, why do we use interfaces? Writing generic algorithms, hiding implementation details, and providing interception points. So what's new, right? Like this is something that you can do with literally every single programming language that has an interface. Why is Go different? Why do we have interfaces that are cooler than anyone else? This, implicit interface satisfaction. What does that mean? This means that we don't have implements. That's the thing, right? If you think about Java, you need in Java for a type to satisfy an interface, you need to add implements that interface. If you do not own the code that defines a type, you're out of luck. You cannot just add implement in there, right? There's ways of solving this, but they're complicated. In Go, you do not have that problem. So let's talk about my first Go project ever. So this is something that I actually implemented. This was actually my second Gophers project. The first one is too shameful to share. It was like something that you should have in like 3 lines of bash. So anyway, so we have func draw, and func draw has a thing that reads a function and it draws it. Amazing. So the way I implemented, I had this package parse that given some string returns a type func. And then that type func has a function eval that given a float returns a float. So basically you're reading a function and then you can call it. That's it. What's inside func? It's magic. You don't care. It's not important. So then the package straw, what it does is imports parse, and it says when you give me a func that you've parsed, I can call it and print the whole thing and generate an image. Cool. So this means that the package straw depends on the package parse. That's how I did it. And if you don't want to do that, if you don't want to have package draw depends on package parse, the way you would do it in a language without implicit satisfaction, with explicit satisfaction, would be you have package draw, package parse, and then some package on top that defines the type that both share. Some interface, probably, right? In Go, you just do this. That's it. There's no point on having an extra package. Why? Because what you can do is replace this import with this. You're saying instead of give me the parsed function, give me something that I can eval. I can call the function eval, right? That's it. So you're actually able to break dependencies across packages and make all of your code much more testable because of this. And I think that this is something that people do not really get at the beginning when they're using Go, and it takes a little bit more time. But this specific thing, implicit interface, is what makes Go interface special. Unless you think about Python and languages like that, which have the same thing, but they're not checked at compile time. So Go is still special. So yeah, interfaces can break dependencies. And this is really powerful. And also a side effect is you should define the interfaces where you use them. If you notice, the evaluator interface is defined where I'm going to use it, right? If you define it in the parse package, if you have type evaluator and then below type func, you're not breaking any dependency. You still have that dependency. So how do I know what types satisfy an interface? And this I'm going to go really fast. Guru, that's the thing. It used to be called Oracle, and they changed the name for obvious reasons. It's a very bad idea to call a Google project Guru, Oracle. So it was changed, and now it's called Guru. And it allows you to do things like this, where I'm saying, hey, so for that rec right there, tell me what are the types that this satisfies. Actually, no. Yeah, no, that I don't know why it's doing this. Oh yeah, rec, because no, that's weird. So basically what I'm doing here is I'm actually asking, hey, tell me all of the types that satisfy the response writer type. Response writer is an interface, has a bunch of methods. What are the types that satisfy that in my Go path? It will tell you all of these things, right? So it will tell you that the HTTP response writer is one of them, popular response is one of them, response is one of them, timer writer is one of them, and also that response writer is a writer. So with this, you can see all of the things directly. This is pretty useful. And actually, it was also integrated recently into GoDoc. So if you do GoDoc-analysis equals pointer, you will get that. So the superpower of Go interfaces is type assertions. Type assertions are really cool and super easy to misuse. So what is a type assertion? This is a type assertion. People call it downcast or something like that. That is wrong, even though it's exactly the same. So v.int, with those parentheses there, what it means is I'm going to get that v, which is an empty interface, and I'm going to use it as an integer. If I do it like that, and it's not an integer, it will panic. And if I do it with a comma OK, with a Boolean, it will return false if that was not the type that I expected. Right? This is super useful. And there's another way of doing this typecast, which is in a switch. You can ooh, that is wrong. That is a switch. Fixed. So, switch. Yeah, thank you. So, lifetime debugging of slides. So yeah, switch of a type. The cases then, instead of being Boolean expressions, they're actually types. So you can say switch type case int default. And even more than that, that's still switch. So you can actually declare a variable. And if you declare a variable, that variable will have different types in every case. And this is something quite useful, because here you can say, well, t in the case int will be of type integer. So you can use it as it was an integer, exactly the same. This is pretty useful depending on what code you're writing. The problem with this is that if you start doing this, you have case int. Cool. What about int32? Oh yeah, case int32. What about int64? Oh yeah, case int64. What about unsigned? Oh yeah, those two. Yeah, and floats, and okay, yeah. So the problem is that this doesn't scale really well. You end up having many, many special cases. And this is something that, if you actually need to do it for integers, you're out of luck. That's how you do it. But if you can do it in a different way, it's much better. And what I recommend is when you're doing this kind of switch, type assertions on switches, instead of doing it to concrete types, you can do them to abstract types. You can do them to interfaces. And now what you're saying is, if this is a type, any type, I don't care, that satisfies the stringer method, then I'm going to get the value, otherwise I'm going to panic or return a Boolean. So now you can do this here, and the fun.stringer that you can see there means that v in here will be of type stringer. So that was wrong too. S.string. Do not copy paste when you're sleep deprived. Not a good idea. So yeah, so fun.stringer, that means that s in there would be stringer, so you can call s.string, right? Which types can go into that? Well, many of them, and we don't really care. If it matches what we expect, it's good. Here, this scales much better, because what you're doing is you're scaling by behavior, not by kind of type. So yeah, there's one more thing, which is we talked about the interception points. And I mentioned that interception points are really powerful, and in the standard library, you see them all the time when you have interfaces. And this is actually something that you see all of the time, especially in stringer, marshaller, and marshaller. So when you have fun.stringer, when you do fun.println, how do you change the behavior of how you print something? You redefine string. Therefore, you satisfy the stringer interface, and you can redefine how something is printed. The same thing can be done for marshaller and marshaller of JSON. If you want to change the way a type is marshaled into JSON, you can define the function JSON marshal or marshal JSON. That's the name of the method. And if you satisfy that, the marshaller will understand that and call that method instead. Right? So there's a lot of different places where you can actually change the behavior of the standard library by redefining methods that make it so you are able to satisfy an interface. And somewhere in the standard library, you will find these things where you're actually checking for different interfaces. This is, for instance, fun.stringer. This is what fun.println will be doing internally, somewhere very hidden in the package. So yeah, use type assertions to extend behaviors, but use them with interfaces as much as possible rather than with concrete types. Our friend, Dave Cheney, that's a picture of him, says, don't just check errors, handle them gracefully, and I recommend doing this. I'm a little bit running out of time, so I'm just going to recommend you watch that talk. The name of the talk is Don't Just Check Errors, Handle Them Gracefully. Literally, that's the name of the talk. So that explains why these slides are cool. So yeah, same thing. And there's one more thing, which is also interfaces provide a way to be able to write code that will work into the future forever. There's a little problem with Go. If you add anything to an interface in Go, you break everyone's code. So you cannot add methods to an interface that is part of the standard library, because then you're breaking the backwards compatibility guarantee for 1.x. So that's a problem, because response writer doesn't allow you to push data. And push is an HTTP2 thing. HTTP2 did not exist when Go reached 1.0. So that's a problem. How do you add a method to an interface that already exists? And this is kind of tricky, but it's actually really cool, so I wanted to show you. So what you do is you do not add it here. Instead, you add the method to your concrete type implementations that get satisfied. So if you had an HTTP2 response, you're actually going to say, oh, I'm going to add that push method to all of your concrete implementations. This doesn't solve anything. But next, you add a new interface with that new method. So you create that interface, pusher, and then in handler, what you can do is that. You can say, hey, the pusher, the interface, the response writer that I'm receiving, is it also a pusher? And this seems like it should not make sense, because the method pusher, the method push in the interface pusher is not a response writer. Therefore, it doesn't make sense. But that's not how it works. The way it works is we're actually checking for the concrete type behind the response writer and checking whether that satisfies the pusher. So if you have an interface, if you have a concrete type that has the method, this will work. And this is something that is like inside of the standard library, and it's kind of hidden and hard to find. But also, this is how you do HTTP2 in Go. If you want to push things to the client before you finish the thing, that's how you do it. Like when you're pushing CSS in JavaScript because you know they're going to need it before they ask for it. That's how you do it in Go. So it's a little bit complicated, and I do not recommend doing this all of the time. But if you have a community of millions of developers that depend on you, and the other option is breaking their code, this is good. Yeah. So yeah, use type assertions to maintain backwards compatibility if you maintain in Go. So in conclusion, Go provides, so interfaces provide generic algorithms. They allow you to hide implementation. They provide interception points. The implicit satisfaction break dependencies. Type assertions allow you to extend behaviors, classify errors, and maintain compatibility. Great. So what about generics? I said we're going to be comparing it to generics, right? So generics in Go. There's a new draft proposed. A new draft proposed is not a proposal. A Go proposal is a very specific thing that might be accepted. A draft cannot be accepted. A draft leads into a proposal that then might be accepted. So we're really far from having this in production, but I think it's worth having a look at it. So it allows you to add type parameters to two things, functions and types. So now functions and types can be generic. What does that mean? Well, it means that you can do this. You can say, you're going to define a method print, a function print, sorry, that receives a slice of t. What is t? It's a type t. And you actually add it in this way. The first time you see it, it looks weird. Especially if the color scheme is not there, it looks even weirder. Because if you think about how you will return multiple parameters, then you have more parentheses, and this starts to look like Lisp. But this is the syntax we have for now. It might change, but for now, this is what it is. So it allows you to use VS as an interface, as a slice of whatever it is, right? This would allow you to fix a couple of problems. So interfaces are not always the best solution for container types, right? If you think about heap, how many of you has used a heap package in the standard library? Okay, I have, and every single time I get it wrong. Because the way it's supposed to be is you append into the beginning, and I always do it to the end, and then I have bugs, and it takes me hours to figure out why, right? This happens because the heap type, what it's doing is it's using the abstract data type approach and saying you need to satisfy this interface. How you do it is up to you. But the problem is that those abstract data types do not represent all of the actions, which means that satisfying the interface is not enough, which means that you need to read the documentation, which I do not, so I fail. So that's a problem. And having the possibility of just defining that interface, defining that type as a generic thing, of saying I have a heap of stuff, whatever it is, that would solve that problem. It would make it much easier for everyone to use the heap package. I invite you to try to use it, and then you tell me. The other option is container ring or container list. These types, what they do is they have an element type that is of type empty interface. So then it is great, except for the little detail that you need to be doing the type assertion all of the time you want to use something. Like if you extract something from the list, oh, this was an integer. This is not too bad. The problem is that you're actually losing the checks at compile time, right? Type safety is gone, and that is a big problem. And generics would fix that too. So generics would make it so these two problems that are a problem of interfaces would be solved. So generics are great, and we should definitely have them. What would this look like? Well, you could have a stack, right? The same stack at the beginning. You could say, I have a stack of type T that is, oh wow, that is bad. That is supposed to be a struct with elements inside, but I removed it coming in the taxi. Okay, so fixed. So now you have this type stack, which is just a slice, and then I'm going to define the methods on stack, and those methods, the receiver is going to be a stack of T. So that's how you write it in the current syntax, which again could change at any point. So you are able to do this. The interesting part is the top returns a T, and that will be the type that you're using. So when you actually use this type, you're saying I'm going to use it with integers. So that will return an integer directly. So you get all of the benefits from the interface from before because you have a generic algorithm, plus you get the static check at compile time, which is great. So is this enough? No, it is not enough. So what if you do this? I'm going to have a max, which it's max of type T. I get a slice of T's, and I find which one is the largest one. Well, what about this here? So if I call it with integers, this will work, because integer is larger than integer works. If I call it with floats, this will work. Great. If I call it with strings, works. Great. If I call it with booleans, is true bigger than false? Maybe. If I call it with a slice of bytes, I'm out of luck. You cannot compare them. So now it's broken, right? So that means that when you're writing this code, you're actually writing something that you could get compile time errors. And if you've ever done generics with C++ and templating, and you've got like these 1,000 lines of error because you're missing a semicolon, I've been there, that's because of this. The fact that an instance could be wrong. So Go tries to fix that with type contracts. And a type contract is something that provides a set of constraints on types, which sounds familiar, right? That's what interfaces do. But the difference is that instead of just doing methods, it actually provides constraints on anything, right? So, comparable type. This is a type that you can compare. This is what it looks like. You're saying this is a comparable type where it receives a value v of type t, and what it does, it checks if v is less than v, which means that somehow that needs to compile. I don't know, I don't care how, but that needs to compile. If you're comparing two slices of bytes, that will not compile, right? So a slice of bytes will not satisfy this contract. And then you can use it like this. You say comparable in that type t is a comparable thing. And now this works, right? So now you can call this, and it will say 1, 2, 3, and it will just work because int is something that you can compare. Great. This is actually something quite nice, and it's very similar to Rust traits, for instance. They're actually quite similar in the same spirit. And with strings, it will also work. A type with length. Same. You say, this is something that I can call len on it, and it returns a variable n of type int. That is the contract. Then I can have my length function and call it with a slice of int or a map, because map also has length, right? So all of these things with interfaces, this is impossible. You cannot do it. So contracts are bringing this new way of providing constraints on top of types. So it's like interfaces, just cooler. So this is what it looks like. The contract writer is a writer that says, this is a writer. Contract string reader is a contract that says, this is a reader. But also the contract length is there, and the contract comparable is there. Interfaces do not allow you to define those two sets on that side, right? So you're able to do quite pretty cool stuff. Also, you can do composition of contracts and all that stuff. So there's a lot of things that you can do. So interfaces are contracts. So interfaces and contracts define sets of types. We agreed on this. It's basically the same idea. But interfaces control on methods and contracts on anything. Therefore, contracts are more powerful. So we should use contracts all the time. No. All interfaces can be represented as contracts. This is the equivalent. So the interface stringer, you can represent it like that. It's a type that has string method. Same thing. It's exactly the same idea, right? These two things are equivalent in syntax and in set of types, but not in behavior. There are things that you cannot represent with Go interfaces. So comparable, for instance, that, oh, it has the less than operator, is not Go interfaces compatible. Also comparable, where you're calling equal, but you're saying, actually, the type that I'm receiving is the same type as I am myself. That is something you cannot do in Go. And it's a little bit of a problem, because it means that if you want to have a comparable, you need to do comparable to what? Empty interface. And then do some checks inside, right? So you're actually getting better coverage of your types by doing this. But this is a problem, because once instantiated, Go contracts disappear. So when you're running your code, Go contracts do not exist. They're not a thing, which means that you're back to whatever you instantiated inside. So if you're instantiating something that is a concrete type, all of the benefits that we have with interfaces, the hiding implementation, providing interception points, all of these nice things that interfaces bring, contracts do not. And because they do not have dynamic dispatching, which has good effects, because this means that the type system will not become more complicated. It will stay the same. At least once you compile something, it will stay exactly the same, which means that Go types or reflect, all of those packages will not need to change, which is nice, because reflect package is already complicated enough without generics. So that's a great thing. But this is a little bit of a problem, because then all of the things that we were saying about interfaces are not possible with contracts. And the last thing is that contracts are, in my opinion, too smart. What do I mean by too smart? 42 pages. That is longer than the Go specification right now. So that is, I mean, it doesn't mean that 42 pages means too complicated, but I read the whole thing. It is long, and it is intense. After reading around 20 pages, there's a phrase that it says, let's take a deeper look. And I was like, God. So yeah, after 20 pages, a deeper look, you know there's a lot of things in there, right? It is really complicated, really complex. And you remember that comparable thing, B equals, like equals that uses the same type. What is the thing that satisfies it? The first one is equal with the method, the receiver is a pointer, it's a T. It receives a T, returns a Boolean. That compiles, so that works. What if the receiver is a pointer? Well, the contract still compiles, so that works. What if the parameter is an empty interface? Well, the contract compiles, so that works. Right? So what are you actually defining is actually way harder to understand than what it seems at first look. First look, it seems like, ooh, great, I understand it. Second look is actually, no, you don't. There's way more complicated things going on in there. Whoops. So to finish with this, basically contracts and interfaces. Interfaces provide all the nice things that we mentioned before, which are super important to Go and that make Go what it is and make the standard library the piece of software that we can extend so easily. But contracts also provide interesting things, generic algorithms and generic types. And they will allow us to write things like a library for concurrency, right? You will not need to write the same like fan in, fan out thing that we've written every single time you need to use it. You could just use a function to do this. You could use the same thing for functional programming. I gave a talk on how to write functional programming in Go, and it was awful because there's not generics, and that will solve it. So this is great, and that's contracts, but actually especially type parameters. Type parameters are great. And also with remote multiplications, if you look at the strings package and the bytes package, they're exactly the same thing, right? Why? Because we don't have generics. Generics would solve that. So in conclusion, interfaces are amazing. I still love them, and I don't think that Go contracts will ever replace them. Type parameters are great, and I want to use them already. Like, please implement it and let me use them. And contracts are great and interesting, but also too smart. And hopefully in the future soon, we will get more iterations and we'll get to something a little more Go-like. Because I think that Go is all about simplicity and contracts are not. Toda. I think we have a couple of minutes for questions. Yeah. Is there any ETA for generics? No, not at all. There's no ETA for the proposal. So yeah, this is the first draft, and this is one of 3 drafts that were done for GOTO that were announced when it was announced that we were working on GOTO. The other 2 are related to errors, values, and error handling. And the interesting thing is that I think that if we do this, then the other 2 do not make sense. Because you'll be able to solve those problems in nicer ways by using monads or whatever you want to use, because you will have generics. So I think that for now, it's something that is created to open the conversation. And it's great that it's going on in there. And I'm happy to participate. But I do not think this will be merged. At least like I'm going to go 1.16. Yeah. Because also, something important is that this is actually backwards compatible, which is very nice. This doesn't mean 2.0. This could be integrated into Go without breaking backwards compatibility, which is great. Yep. Are there any other features that I'm excited about with Go? So one of the things I'm actually excited that has happened is support for WebAssembly. I think that that's super cool, because it means that now I can run Go inside of BigQuery, which is nice. Also, I do not need to write JavaScript, which is nicer. Just because I do not know how to write JavaScript that well. I'm not trashing JavaScript, just to be clear. Also, actually, it's something that, so there's an alternative to these contracts, which is interfaces that would have that would also have fields. That is something that would solve a little bit of the problems that we have right now. So you could say any struct that has a type field, that field ID of type int, or something like that. That could be part of the string, of the interface definition. And that would be really great. There's a proposal for that, but it has not been accepted. And then the other thing, it's actually really related, which is operator overload, but that's probably my C++ background showing. Because I think it's a great thing, but it's also awful. So yeah, I don't know. I think it's an interesting thing I would like to experiment, but probably it's way too early for that, but yeah. And one more thing, actually, hopefully we might have eventually better support for sparse matrices, which means that we could have implementations of TensorFlow that would be efficient. And that's something that I would love to see too. Yeah. Yeah. So yeah, the question is, if Rust solves similar problems to Go, why would I be choosing Go rather than Rust for some problems? I would choose Rust only when memory layout is really, really important, because Rust does that much better than Go. It provides all the tools that you need. But the problem I have with Rust is the concept of memory ownership, which is tied to the fact that it's not garbage collected, is very hard to grasp. So when you're writing code in general, you're going to be fighting the compiler all the time about that little thing. And in Go, that's not a thing, right? So I'd say that in order to write code that works fast, like code that I reach the point where everything just works with Go, I'm much faster than with Rust. It might be part of the fact that I use Rust way less. If I was to choose, like given perfect tooling for all languages, I would probably use Haskell. I think that's one of my favorite languages, and the type system is amazing, right? But at the same time, once you actually start using it, you're like, oh no. So yeah, it's all about like when you actually use a language. I think that the tooling for Go is really good. It's very well done. Like everything just makes sense, and everything is like going for simplicity, and I really appreciate that. So that's probably why. Yeah. Cool. So if you have any more questions, that's my Twitter. So feel free to send me a message or whatever, and I'll be around all day. So thank you.